Hello and welcome to Lecture 4 of Work in Phys 1101, and we have just a few details to clean up, particularly how to deal with friction. Let's start off by looking at a case where we're going to have to consider friction. So here we have some object, a block, whatever, sliding along on a floor, and we know the coefficient of kinetic friction, and we know the mass of the block, and we know it's initially going 5 meters per second, and we want to know how far it slides before it comes to rest. Let me start by defining the system. Well, obviously we want the block in the system because we're interested in its motion. The Earth, well, nothing's going up or down, so we really don't care about whether gravity is an internal or external force, so I'm not going to bother with it. And so then the only other thing is the surface. And I'm going to include the surface, but we'll look in a moment at what happens if we don't. And if you think about the forces on this block as it slides, there's a weight, there's a normal, there's a friction. The weight and the normal are both perpendicular to the motion. They do no work. We don't care about them. And then there's the friction. It's doing work. So the friction force is acting back. And so we know that the work done by that friction force is going to be just the magnitude of that friction force times the distance that the block travels times the cos of the angle between that force and the displacement vector. And if you think about those two vectors, the displacement vector points this way, and the friction force points back this way. And so the angle theta between those two forces is 180 degrees. And you may or may not know that the cosine of 180 degrees is -1. And so this work done by the friction is just negative the friction force magnitude times the magnitude of the displacement. That's it. And what's that going to do? Well, we've already discussed this. That's going to warm things up. It's going to produce thermal energy. So what is going on here is that our system starts off with kinetic energy. And it ends up, all that kinetic energy disappears because the block comes to rest. It is all transformed into thermal energy. And I'm calling those both internal forms of energy because I've included the block in the system and I've included the surface, which is exerting this friction force, which is causing this transformation into thermal energy. Now I'll just comment. The system actually has a whole lot of thermal energy at the start. It has more thermal energy at the end, but we don't care about that initial thermal energy. So really what we're looking at here is a change in thermal energy. That's a minor technicality. So there is our conservation of energy equation. We have Ki equals the change in thermal energy. But now here's where there's a sign issue, because while the work done by friction is negative, the friction force magnitude times the displacement magnitude, so this is a negative number, we know the change in thermal energy is positive. We are producing thermal energy. So this work by friction may be negative, but the amount of thermal energy produced is positive. Okay, so in general, a work done by friction is always equal to the negative of the amount of thermal energy produced. Although I'll say that negative is dicey. Again, I could come up with weird situations with conveyor belts where the work done by friction would be equal to the positive production of thermal energy. But let's not get into that. So now I'm pretty much done. A half mvi squared equals the positive of this, Fk delta x, and we can now solve for delta x. It's just a half mvi squared over Fk. This is one of these simple cases where we're on a flat surface and nothing's accelerating up or down. And so Fk for once is just mu k mg. So we have a half mvi squared over mu k mg. We have mass in the top and bottom. And so now we're pretty much done. We have a half vi, which was 5 meters per second, squared over our coefficient of friction times g. And that is just 25 over 5 is 5.5, so that is 2.5 meters. Let's just look at what would have happened if we hadn't included the surface in the system. So let's go back and think about this again. So this time I'm going to define my system as nothing but the block. And that means the only kind of energy I can have in my system is kinetic energy, because none of the things that are exerting forces are in my system. And so no work is being done by any internal force. And so I'm not going to have any transformations of internal types of energy. But the system still starts out with kinetic energy because the block is in the system and it's certainly moving. And now what happens? Well, we still have this friction and it's still doing work, but it's an external force. And the thing is, now we really do need to say, okay, that is a force which is acting to reduce the energy of the system. The fact that the work is negative tells us that. And so we have negative work by an external force. And we know that at the end, the system has no energy. The kinetic energy entirely disappears. And so now we can rewrite our conservation of energy equation. Now note, the system's energy is not conserved, but this is saying that the system's energy is changing because external work is done. So in other words, energy is being exchanged with the environment. So overall, this is talking about how the energy is conserved. It just isn't conserved in our system. And so that's a half mvi squared, and the work done by the friction, which is negative Fk delta x. Negative Fk delta x equals 0. And just compare that with what we had up here. I will just grab it and pull it down next to the other one. And look, all that's happened is the Fk delta x has been brought over onto this side with a negative, so these are in fact the same equation, and we will get exactly the same answer. Let me just finish up for completeness with one more thing that I did promise some time ago I would show you. And we're not going to focus on this in this course, but I do feel like I should include it for completeness. And it's this issue of work done by a spring force. So we know that if this block, say, slides into this spring and compresses it, the spring is pushing on the block. And so the spring does work on the block. And we've been treating that by keeping track of the spring potential energy. But we should get the same answer if we just calculate a work done by the spring directly. But notice that is a work done by the spring force. And if I just naively go ahead and write, oh, it's, Fs times delta x, which would in fact be the amount of compression of the spring before the block comes to rest, times a cos of an angle between them, and they're parallel, right? It would be back that way, so this would actually come out to a -1, but let's not worry about the sign of this. Okay, but the problem is this Fs is changing. Fs is, and I haven't put a vector symbol, so this is just a magnitude, k delta x. Okay, so that is a straight line on the graph like so. And now let's think about what this does. At any time, Fs is some value, and it's changing from moment to moment. So we don't have any one value of Fs we can put in here, but we've sort of seen this. This is very much like what we saw with impulse, and it turns out that when you have a changing force like this, your work done by any force is the area under the parallel component of that force versus position graph. And that should remind you a lot of impulse. So in this case, if this gets compressed to some delta x final from a compression of 0, the spring was initially uncompressed, then that area is here, and it's a triangle. And so notice that this value here is the force when the spring is fully compressed, so that is k delta x final. And so this area is just going to be a triangle, an area of a triangle, a half the base is just delta xf, and the height is k delta xf, and so this all comes out to a half k delta xf squared. And that's exactly what we already know as a spring potential energy. And so you see it comes out of this more precise definition of a work as an area under a force versus position graph. To finish up, I want to leave you with a general strategy about defining systems, because it's one of the main decisions you make when using energy methods. And remember here that this is all about figuring out what forces are doing work and whether or not it's going to be easier to track that work if the force is an internal force or an external force. Well, obviously anything that's moving and we're interested in its motion, we should include in our system. Otherwise, how are we going to figure out its motion? We should usually include the Earth, and that's so that weight is an internal force, and that allows us to just track work done by weight through changes in the gravitational potential energy. We should also similarly include springs, and that's so that spring forces are internal forces, and so we're going to track the work done by spring forces using changes in spring potential energy. Finally, objects exerting friction, and this is sort of optional. As I just showed you, you can do it either way, but I tend to advocate that you include them. That way you have this nice little category of the thermal energy to keep track of work done by friction. And then you can treat everything else as work done by external forces.